During this lesson, we'll discuss the following topics: definition and explanation of a class in Java. We'll also see how to create a class and we'll understand its structure. And we'll also discuss fields and methods. So, what is a class? In Java, a class is a blueprint for creating objects. It is a blueprint for creating instances of objects with the same data fields and methods. An object is an instance of a class, and it contains its own unique values for data fields and methods. So let's consider an example. Let's say you want to create a blueprint for a car. The blueprint would contain information about the car, such as its make, model, year, and so on. This blueprint is called a class. From this class, you can create instances of the car, each with its own unique values for the data fields. So, in simple terms, a class is a user-defined data type, and an object is an instance of a class. It's like a cookie cutter. You can have multiple cookies cut out from the same cookie cutter, but each cookie is unique and distinct. A class is a blueprint or a template for creating objects. It can have instance variables and methods that define the state and behavior of objects created from it. In order to create a class in Java, you use the keyword class followed by the name of the class. The class name should always start with a capital letter and follow Java naming conventions. Within the class body, you can define instance variables and methods. Here is an example of how to create a class in Java. So we have already defined a package, section 4, lesson 1, example 1. Let's create a new class called car within this package. So we'll right-click, new, Java class, and here we need to type the name of the class. Let's type car. We can double-click class or just press enter, and the class will be created. So we can also just manually create the Java file with name car.java, and within this class we will have to define the following: public class car. This is how the class is defined. Also, please note that we also have a package within which this class is located. So within this class, we want to create two instance variables. First one is int wheels, which will determine amount of wheels this car can contain. And one more variable, let's say string color, which will determine the color of the car. And we also will define one method. It will be void because we don't want this method to return anything. And let's call it honk. So the car needs to make sound, right? And within this method, we'll just print something like beep beep to the console. So the car makes some sound. Okay, so in this example, we've created a class named car. The class has two instance variables, wheels and color, and one method named honk. Let's go over the structure of a class in more detail. The class body is defined within curly braces, within this one. Within the class body, you can define instance variables and methods. Instance variables define the state of the objects created from the class and can have different values for different objects. For example, we can have different amount of wheels for different cars. Maybe some cars can have 6 wheels or, 3 wheels, whatever. Maybe regular cars just have 4 wheels. And the color can be different for each car. It can be black, green, white, whatever. And methods define the behavior of objects created from the class. For instance, this car, when we call the hold method on the object of the car, will print beep beep to the console. It's important to note that the class only serves as a blueprint for objects and doesn't have a state or behavior on its own. To create an object from a class, you use the new keyword and call the constructor of the class. The constructor is a special method that is automatically called when an object is created and is used to initialize the state of the object. We will discuss constructors later in our future lessons. Let's discuss fields in Java classes. Fields are also known as member variables or instance variables. They are used to store data for each object of a class. Let's start with an example of a class called student. The class contains fields such as name, roll number, and marks. Here, name, roll number, and marks are the fields of the student class. These fields are used to store the data for each student object. For instance, we can have different students. One of them has name John, roll number 2, and marks, let's say 5. And another one has name Brad, roll number 10, and marks 5 as well, for example. Let's see another example of a class called car. The class contains fields such as model, make, and year. Here, model, make, and year are the fields of the car class. These fields are used to store the data for each car object. It's important to note that fields can have any data type, including primitives like int, float, double, or reference types like string, object, or custom classes. Now that you have an understanding of fields, let's see how we can initialize them. Fields can be initialized in several ways. The most common way to initialize fields is in the constructor of the class, but we'll cover constructors in more detail in a later lesson. Fields can also be initialized directly when they are declared. So here's an example. We have a class called circle, and here the fields radius and color are directly initialized to 1 and red respectively. In addition to constructor and direct initialization, fields can also be initialized using instance initializer blocks. An instance initializer block is a block of code that is executed when an object of the class is created. So let's see an example. We have a class book with two fields, title and pages. And title and pages both initialized within the initializer block. So here the instance initializer block initializes the fields title and pages to unknown and 0 respectively. Now that you have a good understanding of fields, it's time to put this knowledge to use. Try to create a class with fields and initialize them in different ways. In the next part of this lesson, we will be discussing methods in Java classes, so stay tuned. First, let's recall that a class is a blueprint for creating objects which defines the properties and behavior of an object. Now we will see how to define the behavior of an object using methods in Java. As you remember, a method is a block of code that performs a specific task. It is defined inside a class and can be invoked or called by creating an object of the class and using the dot operator. The basic syntax for creating a method in a class is as follows. You can see it at the example. And here in this example, access modifier is an optional field that defines the visibility of the method. The return type specifies the type of value the method returns. The method name is the name of the method, and parameter list is a list of parameters that can be passed to the method. Let's see an example of methods in a class. First, let's talk about the car class itself. This class is a template for creating car objects. Each car object will have its own speed and gear. So here we have two instance variables, speed and gear. These are like characteristics of our car object. The speed variable keeps track of how fast the car is going, and gear represents the current gear of the car. Every car object will have its own speed and gear. Next, we have several methods in the car class. Methods are like actions or behaviors that the object can perform. Let's break them down. First one is the change gear. This method allows us to change the gear of the class. It takes one parameter, new gear, as you can see here, which is the gear we want to set. When we call this method, it updates the gear variable with the new value, new gear. Next, we have a speedup method. This method increases the speed of the car. It takes one parameter, increment, which tells us by how much we want to increase the speed. It then adds this increment to the current speed, as you can see here. Next one, we have apply brakes method. This method decreases the speed of the car. It takes one parameter decrement, which is the amount by which we want to reduce the speed. It subtracts this decrement from the current speed. And lastly, we have a getSpeed method. The getSpeed method returns the current speed of the car. It doesn't take any parameters. As you can see, the parameters list is empty and simply returns the value of the speed variable. In conclusion, methods are a key aspect of Java classes as they define the behavior of an object. They can be used to perform specific tasks, return values, or take parameters. By understanding how to use methods, we can write more complex and dynamic programs that can interact with objects in meaningful ways. During this lesson, we will discuss the following topics: the definition and explanation of an object in Java. We'll also see how to create an object from a class. We'll understand the relationship between classes and objects. And we'll see how to use the dot operator to access object methods and variables. And also we'll understand the difference between an object's reference and its value. Okay, so an object in Java is an instance of a class. It represents a real-world entity and encapsulates its state and behavior. Simply put, an object is a combination of data and methods that operate on that data. For example, let's consider a class called car. A car can have properties such as its make, model, year, and color. It can also perform actions such as starting driving and stopping and so on. These properties and actions can be represented as variables and methods within the car class. A single instance of the car class is an object of the car class. For example, you might have an object called myCar, which is a car object and represents your own car. In summary, an object in Java is an instance of a class and represents a real-world entity with both data and behavior. Understanding this concept is crucial to developing effective and efficient object-oriented Java programs. Now that we understand what an object is, let's learn how to create one. we create an object using the new operator and the constructor of the class. The syntax for creating an object is as follows. You can see it at the example. Here, we declare a variable object name of type class name, and we create a new object using the new operator and the constructor of the class name class. Let's take a look at a code example to better understand this process. Let's say we have a class person. We have two instance variables here, name and age. These variables store the name and age of the person respectively. Each person object we create will have its own separate name and age. Next, we have a main class, within which we have a main method. And let's see what happens here in the main method. So here, in these two lines, we created two objects, person1 and person2. Both are instances of the person class, as you can see. But even they are created from the same class, each object is independent and has its own separate state. So in next two lines, we assign different values to these objects using the assignment operator, and we can access all the fields from the person1 object and person2 as well using the dot operator. So here we print person1 dot name equals John. It means that the name field of the person1 object will be now changed to John. And the same, we update the age. So it means that the age field of the person1 object will be changed to 30. So we assigned in the new value. Just a reminder that all the fields will be assigned with default values. And same for arrays, default values are the following. For numbers, it's 0, for booleans, it's false, and for references, it's null. So by default, since name is a reference type, it's initialized with null, and age, since it's numerical type, it's int, it will be initialized with 0. And after that, in these two lines, we change values of these fields of the person1 object. It means that person2 will remain untouched because it's completely separate object. And in next two lines, we do the very same thing with person2 object, but we assign different values. Here we assign the name Jane and the age to 25. So as you can see, person1 and person2 are created from the same person class, but they maintain their own separate state. This means that person1 has the name John and age 30, and person2 has the name Jane and age 25. This demonstrates how objects from the same class can hold different data. And to see this in action, let's print out the details of each person. So here we have two system out print line calls for person1 name and age, and for the person2 name and age respectively. So this confirms that person1 and person2 each maintain their own state. So let's run the program and verify. Okay, so as you can see, person1 name is John, the age is 30, and for the person2 name is Jane and age is 25. As we learned in the previous lesson, a class defines the blueprint for objects. In other words, classes are the templates that we can use to create objects. But what exactly is an object, and how does it relate to a class? An object is an instance of a class. When we create an object from a class, we are creating a real-world representation of the class. For example, if we have a class called person, we could create an object from the class that represents a specific person, like John Doe. This relationship between classes and objects is similar to relationship between a cookie cutter and a cookie. The cookie cutter defines the shape and size of the cookie, just like a class defines the properties and behavior of an object. When we use the cookie cutter to make a cookie, we are creating an instance of the cookie cutter. Just like when we create an object from a class, we're creating an instance of that class. Let's look at an example to further illustrate this relationship. So consider the following class. We have a class dog, within which we have two fields, breed and age. Also, we have a method called bark that prints woof to the console. Also, as you can see, we have a main class within which we have a main method. So let's create an object from the dog class like this. Dog, this is a class name. Then we need to give a name to variable we are going to define. Let's call it my dog. My dog. And we need to use a new operator to create a new instance of the dog class and the class name and parentheses. This is how we call the constructor of the dog class. We'll discuss constructors later. For the time being, let's just use empty parentheses. So with this line of code, we are creating an instance of the dog class, which is an object that we've named my dog. We can access properties and behaviors of this object by using the dot operator. For example, let's say my dog dot. This is an operator we are using to access methods and fields of the my dog object. Let's, for instance, assign a breed to this dog to Labrador. Let's also assign the age to 3, and let's call the bark method on the my dog object. So in this code, we are setting the breed and age properties of the my dog object, and we are calling the bark method, which will print woof to the console. Let's run the program and see that woof is printed to the console. Okay, it's printed to the console because we called the bark method, and this is the only point at which something is printed to the console. So, to recap, classes and objects have a very important relationship in object-oriented programming. Classes define the blueprint for objects, and objects are instances of classes that represent real-world entities. When we create an object from a class, we are creating an instance of that class that we can interact with and modify. Let's dive into the difference between an object's reference and its value. In Java, an object is a dynamic instance of a class created at runtime. When we create an object, the object takes up space in memory and we get a reference to that memory space. This reference points to the actual object in memory. The reference is used to access the methods and fields of the object. For example, consider the following code. Here we have created a class called car with two fields, model year, which is int, and model name, which is string. We also have a main class with the main method as usual, and here in the main class we created an object of the car class using the new operator and assigned it to the variable called myCar. Then we assign the model year to the myCar object to 1969, and we also assign the model name to the myCar object to Mustang. Then we created another variable called another car and assign it to myCar. Now, myCar and another car both refer to the same object in memory. It means if we change the value of one of the fields in the object through myCar, the very same change will be reflected in the object when we access it through another car. This is because both myCar and another car, as I mentioned, refer to the same object in memory. So when we print the model name and year both for myCar and another car, they will be the same. We will run the program after I explain the whole example and see the output. And however, if we assign a new object to myCar will now refer to the new object, but another car will still refer to the original object. The two references are now pointing to two different objects in memory. So if we now modify myCar objects through updating the model year and model name, it will now not be reflected at the another car object because they are now pointing at different objects in memory. So when we print myCar model name and another car model name, they will be now different. So let's run the program and see the output. Okay, so as you can see, during the first invocation, myCar model name is Mustang and another car model name is also Mustang. But after that, we created a new car object and assigned it a model name Camaro and model year 2010. And now, since myCar and another car in this part of the example pointing to the different objects in memory, you can see that the model name and year are different between these objects. So to summarize, an object's reference is a variable that points to the actual object in memory. The value of an object is the actual data stored in the object. The reference can change and point to a different object, but the value of an object can only be changed by modifying its fields. During this lesson, we'll discuss the following topics: the static keyword, access modifiers, initialization blocks, nested classes, and getters and setters. Let's first discuss the static keyword in Java. The static keyword in Java is used to indicate that a member belongs to a class rather than to an instance of the class. In other words, a static member is shared by all objects of the class rather than being unique to a specific object. To understand this better, let's look at a code example. Let's say we have a class called MathHelper that contains a static method that returns the square of a number. In order to specify that the method is static, we need to add a static modifier before the return type of the method. So the code will look in the following way. Notice how the keyword static is used before the method square. This indicates that the method belongs to the class MathHelper and not to an instance of this class. To call this static method, we don't need to create an instance of the MathHelper class. Instead, we can call it directly using the class name in the following way. So we have a main class with the main method as usual, and we create a result variable of type int, and we assign it the following value: MathHelper, this is the class name, dot square. So as you can see, we don't need to create an instance of the MathHelper class using the new operator. We just can access the square method using the dot operator on the MathHelper class. So in this example, we called the static method square on the massHelper class without creating an instance of it. And this is because the method square is static method and belongs to the class, not to an instance. So let's run the program and see the output. I didn't dive deep into the implementation of the square method because it's not so important. It just calculates the square of the number. So the square of 5 is 25, as you can see. So the method was successfully called, even if we didn't create an object of the massHelper class. Apart from methods, static keyword can also be used with variables, which are called static variables or class variables. They are shared by all instances of the class and are accessed using the class name, just like static methods. Here is an example. Let's update the massHelper class in the following way. So in this example, the static variable p belongs to massHelper class. So we have defined a static variable called p within the massHelper class. So this variable can be accessed using the class name in the following way. So we have a main class with the main method, and we can print the value of p in the following way. We can just use massHelper, this is a class name, dot p. Because p is a static variable and can be accessed without creating an object of the massHelper, we can easily access it in the following way. So let's now run the program and see that p is now printed to the console. Okay, we can see that the value of p is 3.14. In summary, the static keyword in Java is used to indicate that a member belongs to a class rather than to an instance of the class. This means that static members are shared by all objects of the class and can be accessed using the class name without creating an instance of the class. Let's now dive into the topic of access modifiers in Java. Access modifiers determine the accessibility of fields and methods in a class, and they are essential part of encapsulation, one of the four fundamental concepts of object-oriented programming. In Java, there are four access modifiers: public, private, protected, and default. So let's discuss each of them one by one. First, let's look at the public access modifier. If a field or method is declared public, it can be accessed from anywhere in the code, both inside and outside the class. For example, consider the following code. So in this code, the field ID and the displayID method are declared as public. So we specified the access modifier before the return type of the method and before the type of the field. So they can be accessed from the main class, which we declared separately. So if you run the code, it will display that ID is 1001. So we can access the ID and display ID method from outside of the student class because they are declared as public. So let's run the program and see the output. Okay, so we can see that ID is 1001. And for public methods, it's not even valuable that the main class is within or not within the very same package as a student class. So we can create one more package here, let's call it main. And let's move the main class to this package. Okay, so now the main class, as you can see here, has a different package than a student class. But it's not a problem for us because we declared the field ID and the method displayID as public. So they are still visible within the main class. So let's run the program again and see that nothing is broken now. Okay, we can still see the ID is 1001. Now let's look at the private access modifier. If a field or method is declared private, it can only be accessed within the class in which it's declared. For example, consider the following code. So we have a student class with field ID, which is private, and also we have a private method called display ID. As you can see that within the display ID method, we can access the ID field with no issues. But outside of the student class, for example, in the main method, we cannot access the ID field and we also cannot access the display ID method. This is because both of them are declared as private. So let's hover them, and the IDE helps us and says that ID has private access in the student class, and same for the display ID method. It says that display ID has private access in the student class. So if we try to run this code, it will give us a compile time error because the ID field and the display ID method cannot be accessed from the main class. They cannot be accessed outside of the student class. So let's try to run it. Okay, as you can see, it says that ID has private access in the student class. Lastly, let's look at the default access modifier. The default access modifier, also known as package private, is used when no access modifier is specified. By default, a field or method with the default access modifier is only accessible within the same package as the class. Let's take a look at a code example to better understand the default access modifier. So consider the following class person. In this example, the age field and the printAge method both have the default access modifier because nothing is specified here. So we didn't specify the modifier, and by default it's package private or default. And this means that both age field and printAge method are only accessible within the same package as the person class, and package is specified here at the very top of the file. So current package is section 4 lesson 3 example 5. And if we tried to access the age field or printAge method from another package, we would receive a compile time error. Okay, so we have a main class with the main method within the very same package, section 4, lesson 3, example 5. And it means that we are able to access the age and the printAge from this main method, since we are in the same package. So let's run this program and see the output. Okay, we can see that age is 30. We are easily access the age and the printAge. And let's now do the following. Let's create a new package, and let's call it main. And let's move the main class to this main package. Okay. And as you can see now, it's located in a different package, and age and printAge are no longer accessible because we are in a different package. So if we try to run the program, we will receive a compile time error. Let's try to run it. Okay, so we can see that age is not public in the person class and cannot be accessed from outside package. Now, if we want to make the age field and printAge method accessible from another package, we could simply change the access modifier to public. So if we update the access modifier to public here and here as well, then let's go back to the main class and we can see that both fields are now accessible, and we can simply run the program and it will compile with no issues. Okay, so that's it for the default modifier. Please note that there is also a protected access modifier, but we will discuss the protected access modifier later because it requires more background knowledge. Now, let's discuss initialization blocks. Initialization blocks are a way of initializing the state of an object when it's created. There are two types of initialization blocks in Java. instance initialization blocks, and static initialization blocks. Instance initialization blocks are used to initialize instance variables of a class. They are executed when an object is created and before the constructor is called. Let's take a look at an example to see how instance initialization blocks work. So, in this example, we have a class called example with two instance variables, x and y. And also we have an instance initialization block that initializes x with 10 and y with 20. So this is the syntax of the instance initialization block. Also within this class, we have a constructor. We didn't discuss constructors yet, and we will cover them in detail in our future lessons. But just for this example, you can note that constructor is kind of method that is called when the object is being created. So when we create a new example object, this method will be called and this system out print line will be triggered. So the following will be printed to the console. And we also have a main method that simply creates a new instance of the example class. So when we run this program, the output will be in constructor x equals 10 and y equals 20. And this shows that the instance initialization block is executed before the constructor is called. And the values of x and y have been successfully initialized. So let's run the program and see the output. Okay, so we can see that in constructor x equals 10, y equals 20. Static initialization blocks, on the other hand, are used to initialize static variables of a class. They are executed only once when the class is loaded into memory and before any object of the class is created. Let's take a look at an example to see how static initialization blocks work. In this example, we have a class example with two static variables, x and y. And also we have a static initialization block. The syntax of the static initialization block is pretty straightforward. So you just need to use the word static before the initialization block. So within our static initialization block, we set value 10 to the variable x and value 20 to the variable y. Also, we have a main class with a main method that prints out the x and y to the console. So when we run this program, the output will be 10 and 20, which shows that the static initialization block is executed only once when the class is loaded into memory, and that the values of x and y have been successfully initialized. So let's run the program and confirm it. Okay, we can see 10 and 20, which is value of x and y respectively. That concludes our discussion on initialization blocks, and it's important to understand the difference between instance and static initialization blocks and when to use each other. This will allow you to write cleaner and more organized code. Let's discuss nested classes in Java. A nested class is a class that is declared inside another class. Nested classes can be used to group related classes together to create a better structure in your code. It can also be used to create a more secure implementation of a class. In this lesson, we will cover the different types of nested classes and show you how to use them in your code. There are two main types of nested classes in Java: static nested classes and inner classes. Static nested classes are declared using the static keyword. They are called static nested classes because they are associated with the outer class, not with a particular instance of the outer class. This means that you don't need an instance of the outer class to create an instance of a static nested class. Here is an example of a static nested class in Java. So what is happening here? We have an outer class, and inside it we have declared a static class called nested class. The nested class has a method called printMessage that simply prints out a message to the console. And also we have a main class. Since the nested class is static, we don't need to create an instance of the outer class to access it. Instead, we can directly access nested class using the name of the outer class. So we do the following: new outer class dot nested class. So let's break it down. In this part of this line, we are saying that nested class is of type outer class dot nested class. And in this part of line, we are saying that outer class dot nested class creates an instance of the nested class. And afterwards, nested class dot print message just prints the hello from the static nested class to the console. So let's run the program and see the output. Okay, so we can see that hello from static nested class was printed to the console. Inner classes, on the other hand, are declared without the static keyword. An instance of an inner class is always associated with an instance of the outer class. This means that you need to create an instance of the outer class before you can create an instance of an inner class. And here is an example of an inner class in Java. So we have a class called outer class, and within this class we declare an inner class. Please note that there is no static keyword. That's why this is an inner class. And within the inner class, we have defined a printMessage method, which simply prints the following string to the console. Okay, to create an instance of an inner class, you first need to create an instance of the outer class. So let's see how it works. We have a main class with the main method. So here we want to create an instance of the inner class and call the printMessage method on the inner class instance. In order to do that, first, in the following line, we need to create an instance of the outer class. And after that, we declare a variable of type outer class.inner class. We call it inner class. And we use the following construction. Outer class, this is an instance of the outer class, dot new inner class. Since the inner class is not static, we need to use the outer class instance to create an instance of the inner class. So afterwards, we are able to call the printMessage method on the inner class object. Let's run this program and see what it prints to the console. Okay, so we can see that hello from the inner class has been successfully printed to the console. Another type of inner class is the local inner class. A local inner class is a class declared within a method. A local inner class can only be used within the method in which it's declared. And here is an example of a local inner class in Java. So in this example, we have a class called outer class with a method printMessage. Inside this method, we define a local inner class called local inner class. This local inner class has its own print message method. This method prints hello from the local inner class to the console. After the local inner class is defined, we create an instance of this class and call its print message method. The key point to understand about local inner classes is their scope. The local inner class is only accessible within the print message method. You cannot use this class anywhere else in the outer class or outside it. You define a local inner class just like any other class, but it stays hidden and is only useful within the method it's defined in. We also have a main class within which we have a main method where we create a new instance of the outer class and call the print message method. So when we call the print message method, then we'll create a new instance of the local inner class, which is visible only within this method, and we'll call the print message of this class. So let's run the program and see the output. As you can see, hello from the local inner class has been printed to the console. In conclusion, nested classes can help you to organize your code and improve the structure of your classes. They also provide a secure implementation of your classes. You can choose between static nested classes, inner classes, and local inner classes, depending on your needs. And now let's dive into a very important aspect of object-oriented programming, getters and setters. Getters and setters are methods that provide a way to access and modify the fields of a class respectively. They are used to control access to the data of an object and to maintain the integrity of the object's data. So let's see in action by taking a simple example. Consider the class person. Let's say we want to create fields for the person's name and age. And we want to restrict access to these fields so that they can only be modified through setter methods. And here how the class would look like. So we have a person class, we have two private fields, string name and int age. Since they are private, they can only be accessed within the person class. We have created two public getter methods, getName and getAge, that return the values of the name and the age fields respectively. And we have also created two public setter methods, setName and setAge, that allow us to set the values of the name and age fields. Note that the age field has simple validation to ensure that the age is not negative. This is a common practice to maintain the integrity of the data of an object. So, with these getters and setters, we can access and modify the values of the fields from outside the class, but in a controlled way. We can create an object of the person class, set its name and age, and get its name and age in the following way. So we have a main class with the main method. So here we create a new instance of the person class and assign it to the person variable. Then we set the name to this person using the setter, and in the same way we set the age to this person using the setAge method. Finally, we print the name and the age using the getters, getName and getAge, so we print them to the console. So let's run the program and see the output. Okay, we can see that the name is John Doe, and this is what exactly we set using the setter. The age is 30, and this is what we set using this setter. And that's it. Getters and setters are a fundamental part of object-oriented programming, and they are used to provide controlled access to the fields of a class. By using getters and setters, you can ensure that the data of an object remains consistent and protected. Just note that you can update the logic of the getters and setters or just remove them entirely if you don't want to allow the age to be set externally. You can just remove the set age. Or if you don't want to allow the name to be get externally, you can also remove the getName method. So during this lesson, we will discuss the following topics: the definition and explanation of constructors in Java. We'll also discuss types of constructors like default and parameterized. We'll discuss this keyword, and we'll also see how constructors are used when creating objects. Constructors are a special type of method in Java that are used to initialize objects. Let's dive into the first part of this lesson and start by understanding what constructors are and what they are used for. So, as I mentioned, in Java, a constructor is a special type of method that is used to initialize objects. When an object is created, its constructor is called automatically to set the initial values of its instance variables. The constructor's name is the same as the class name, and it has no return type, not even void. Let's consider an example to understand this better. Consider a class named person. It has two instance variables, name and age. When we create an object of the person class, we want to set the name and age of that person. This is where constructors come into play. With the help of a constructor, we can initialize the values of the instance variables when an object is created. So here's how we can define a constructor for the person class. So in this example, the constructor takes two parameters, name and age, and set the values of the instance variables, name and age, accordingly. So notice that the constructor's name is the same as the class name, person, and it has no return type. Also, please note that we specified the access modifier here, and our constructor is public because we want it to be accessible from everywhere. This keyword in Java is used to refer to the current object of a class. It can be used to distinguish between class variables and instance variables that have the same name. This is useful when you want to access the instance variables of an object and not the class variables. In the constructor of the person class, we use this keyword to distinguish between the instance variables name and age and the constructor parameters name and age. So we want to distinguish between this and this. So when we are using this keyword, then we mean that we want to access exactly this name, not the name that we passed in the parameters. So by using this .name equals name, we are saying that we want to assign the value of the constructor parameter name to the instance variable name. When you create an object in Java, you need to use the new operator in combination with a constructor. For example, we have a main class, and here we want to create a person object by calling the constructor we just defined. So here we are creating an instance of the person class passing in the values John and 30 as parameters. The constructor will then initialize the instance variables name and age with these values. And finally, we print the person's name and age. So let's run the program and see the output. Okay, so we can see that name and age were successfully printed to the console. In summary, constructors are special methods in Java that are used to initialize objects. They are called automatically when an object is created and they have no return type. Their name is the same as the class name, and they can be parameterized or not parameterized. In the next part, we'll be discussing the two types of constructors in Java: default and parameterized. A parameterized constructor is one that you define explicitly in your class, with parameters to initialize instance variables with given values. It allows you to provide different values to distinct objects. A default constructor is a constructor that is automatically provided by Java if no other constructors are explicitly defined in a class. It has no parameters. It initializes the object with default values. For example, null for objects, 0 for int, false for boolean, and etc. If you define any constructor for your class, Java doesn't provide a default constructor. Consider the following example. In this example, we have defined a class called car, and also we have defined a parameterized constructor that takes three arguments: make, model, and year, and uses these arguments to initialize the instance variables of the same name. So it initializes the make, the model, and the year. This allows us to create objects with specific values for these variables when we call the constructor. And finally, we have a printinfo method that simply prints the make, the model, and the year to the console. Also, we have a main class within which we create a car object using the newly created parameterized constructor. So as I just mentioned, this constructor takes in three arguments: the make, model, and year. And here within the main method, we use exactly this parameterized constructor to initialize the car object with the make, Volkswagen, the model, Jetta, and the year, 2016. And finally, we print the info of this car. Let's run the program and see the output. Okay, we can see that all of the parameters were successfully printed to the console. On the other hand, a default constructor is a constructor that is automatically created by the Java compiler if no other constructors are explicitly defined in a class. It has no arguments and provides the default values for the object's instance variables. For example, we modified the car class in the following way. We still have the make, model, and the year defined in the car class, but we removed the parameterized constructor. So, as you can see, there is no constructor defined in this class. However, Java automatically generates a default constructor for this class that initializes all the instance variables to their default values. In this case, the make, model, and year variables would be set to null, null, and 0 respectively. Make will be null since it has the string type, and string is a reference data type. For reference data types, the default value is null. Year is a primitive data type, it's a number. So for year, the default value will be 0. If we had a Boolean variable, it would be initialized with false. So I left a comment here that under the hood, Java will generate the following constructor: public car with this make equals null, this model equals null, and year equals 0. And as you can see, it doesn't have any parameters. Okay, so let's go to the main class where we have a main method. In this method, we create a car object using the default constructor. Afterwards, we print the car info. So let's run this program and see what is printed to the console. As you can see, the default values are printed to the console. It's null for string and 0 for int. Please note that if you define at least one constructor, Java will not generate the default constructor. In Java, you can have more than one constructor in a class, but they must have different parameter lists. This is known as constructor overloading. So consider the following class called coordinates. It has two instance variables, x and y. We have created two constructors. First constructor doesn't take any parameters and sets value 10 to x and value 15 to y. Second constructor is parameterized and sets the provided values to x and y. And also the coordinate class contains the printinfo method just to print the x and y to the console. Let's go to the main class where we have the main method as usual, and here we create two objects. First object has name coordinates1 and it's created using the not parameterized constructor. The second object is created using the parameterized constructor. And we also print the info of each object. So let's run the program and see the output. Okay, as you can see, the first print statement resulted in the following output, 10 and 15. This is because we created the first object using the not parameterized constructor. And in this constructor, we set value 10 to x and value 15 to y. And this is what was printed to the console. And the second line is the result of the output of the coordinates2 object, which was created using the parameterized constructor. And we specified the following values, 25 and 40 respectively. So this is what was printed to the console. This keyword can also be used to call other constructors within a class. This is known as constructor chaining and can be used to create multiple constructors that perform similar operations with different parameters. Let's take another example to demonstrate constructor chaining. Consider a class called rectangle with instance variables width and height. The rectangle class contains two constructors. The first constructor, public rectangle, has no parameters and calls the second constructor, public rectangle, that takes the width and height by using this and providing values for width and height. This allows us to create a rectangle object with default values if no parameters are passed in, or to create a rectangle object with custom values if parameters are passed in. This keyword is a powerful tool in Java that allows us to refer to the current objects, distinguish between class variables and instance variables with the same name, and perform constructor chaining. So also, as you can see, the rectangle class contains the printinfo method that simply prints the width and height to the console. Let's go to the main class, and here within the main method, we first create a rectangle1 variable of type rectangle. using the not parameterized constructor and print its info. And afterwards, we create a rectangle2 object using the parameterized constructor and print its info. So let's run the program and see what is printed to the console. As you can see, width equals 0, height equals 0 was printed to the console because we created the rectangle1 object using the not parameterized constructor. So within the not parameterized constructor, we called the parameterized constructor with parameters 0, 0. So this is something like if we created this object in the following way. And next line is width equals 5 and height equals 10 was printed because this object was created using the parameterized constructor, and we passed values 5 and 10 respectively to this constructor. During this lesson, we'll discuss the following topics: the overview of interfaces in Java. We'll also see how to define an interface. We'll see how to implement an interface. I will discuss extending an interface and default and static methods in interfaces. So, an interface in Java is a blueprint for a class. It defines a set of methods that a class must implement, but it doesn't provide any implementation. An interface acts as a contract between the class and the outside world. It defines what the class is capable of doing, but not how it does it. Interfaces are used in Java to achieve abstraction. Abstraction means hiding the implementation details of a class and showing only the necessary information to the outside world. This allows us to create objects that have a similar behavior, even if their underlying implementation is different. For example, let's consider the case of a car. A car is an abstract concept and can be implemented in different ways, such as a sports car, a sedan, or a crossover. Each implementation of a car may have different features and characteristics, but they all share the same basic behavior, such as starting the engine, accelerating, and braking. We can define this basic behavior in an interface called car, and then use it to create objects that implement this behavior. So let's take a look at an example code. Let's create a car interface. Right-click on the package, New, Java class. Here we can click on the interface and let's type car. Enter. As you can see, public interface car was created, and let's now define 3 methods within the interface car. The first method will be wait start engine. The second one will be accelerate. And finally, let's define the method brake. So in this code, we have defined an interface car with 3 methods: start engine, accelerate, and brake. The class that implements this interface must provide a concrete implementation for these methods. So as you can see here, all of the methods don't contain the implementation. And also, you can mention that they don't have an access modifiers. This is because by default, within interfaces, all of the methods have public access modifier. In this part of the lesson, we have covered the basic concept of interfaces in Java and how they are used to achieve abstraction. And in the next parts of this lesson, we will dive deeper into how to define, implement, and extend interfaces in Java. An interface is a blueprint for a class, specifying a set of methods that a class must implement. In other words, an interface defines a set of methods that a class must contain in order to be considered a part of that interface. This is done to enforce a certain structure and behavior on the class that implements the interface. A class can implement multiple interfaces, and this allows you to build complex systems in a modular and flexible manner. To define an interface in Java, we use the keyword interface, followed by the name of the interface. Here's an example. You can see it on the screen. In this example, the interface shape defines two methods, getArea and getPerimeter, that any class that implements this interface must implement. The methods in an interface are implicitly abstract, meaning they don't have a body, only a signature. This means that the class implementing the interface must provide the implementation of these methods. Under the hood, all methods in interfaces are public, so we can write method definitions without the access modifier. It's important to note that an interface can only contain method signatures and constants. It cannot contain instance variables or instance methods with a body. To implement an interface in Java, we need to use the implements keyword followed by the interface name in the class declaration. A class can implement multiple interfaces, and each interface can contain methods that the class must provide a definition for. So here is an example. In this example, the drivable interface contains two methods, start and stop. Also, we have a car class that implements the drivable interface. So in order to specify that the car class implements the drivable interface, we need to specify the implements keyword after the class name, and after the implements keyword, we need to specify the interface name. So the car class implements the drivable interface and provides definitions for both methods. By using the override notation, we indicate that the methods in the class are intended to override the methods in the interface. This helps ensure that the methods have the correct signature and also makes the code more readable. It's important to note that when a class implements an interface, it must provide definitions for all methods defined in the interface. If the class doesn't provide a definition for a method, it will not compile. This is one of the key benefits of interfaces, as it helps enforce consistent behavior across different objects that implement the same interface. So if I remove, for example, the stop method, I will not be able to compile the code because, as you can see, compiler will say that class car must either be declared abstract, we'll discuss abstract classes later, or implement abstract method stop in drivable interface. So let's return the stop method. Okay, so as you can see, within the start method, we simply print the car has started to the console, and within the stop method, we simply print that car has stopped to the console. We also have a main class with a main method. Within the main method, we create a variable of type drivable, this is an interface type, and assign it the following value, new car. Since car implements drivable, we are able to do that and compiler will not argue. After that, we call the start method on the drivable variable. And afterwards we call the stop method. So let's run the program and see the output. As you can see, car has started and car has stopped messages were successfully printed to the console. And they were printed because the object that we are referring to has type car. And within the car, we have the following implementations. And drivable just provides an interface. It provides us start and stop methods that we must implement in all the classes that implement the drivable interface. In summary, implementing an interface in Java requires a class to use the implements keyword, followed by the interface name in the class declaration. The class must then provide definitions for all methods defined in the interface and use the override annotation to indicate that these definitions are intended to override the methods in the interface. The override annotation is not mandatory, but I recommend you to use it because it will be easier to read and maintain your code. In Java, a class can implement multiple interfaces at the same time. So let's say we have the interface called drawable that contains the method draw. So it means that we can draw something. We have one more interface called movable with single method called move, and it means that we can simply move the object. Also, we have a rectangle class that wants to have the ability to both draw and move. So it implements both the drawable interface and the movable interface. In order to specify that the class implements multiple interfaces, we need to specify the comma-separated list of interface names after the implements keyword. So here is how the rectangle class looks like. It overrides the draw method in the following way. It simply prints the drawing a rectangle to the console, and it also overrides the move method in the following way. It simply prints moving a rectangle to the console. So as you can see, we define the two interfaces, drawable and movable, which both contain methods that need to be implemented by the rectangle class. The class rectangle implements both of these interfaces by using the keyword implements and providing implementations for the methods defined in each interface. In this way, we can build complex functionality by composing different functionalities provided by multiple interfaces. So let's now see it in action and open the main class with the main method. Here, we define a variable of the type rectangle with name rectangle. In the following way, we simply use the constructor of the rectangle. And afterwards, we call both draw and move methods on the rectangle object. Let's now run the program and see the output. As you can see, drawing a rectangle and moving a rectangle messages were successfully printed to the console. An interface in Java can extend another interface, allowing it to inherit all of its methods. This allows us to create new interfaces that are based on existing ones and to build up a hierarchy of abstractions. To extend an interface, we use the extends keyword followed by the name of the interface that we want to extend. Let's take a look at the example. So in this example, we have defined an interface called animal with a single method called makeSound. We want to extend this interface to create a new interface called mammal. So let's go to the mammal interface, and here we can see that we use the extends keyword to specify that mammal interface extends the animal interface. Our new mammal interface contains new method called giveBirth. By extending the animal interface, the mammal interface inherits all of its methods. This means that any class that implements the mammal interface must implement both the makeSound method from the animal and giveBirth method from the mammal. We also have a class called dog that implements mammal interface. We must implement both makeSound and giveBirth methods in the dog class. So here are the implementations. Within the makeSound, we simply print bark to the console, and within the giveBirth, we simply print dog gives birth to the console. Let's now see how to create an object of the dog. So here in the main class and the main method, we create a new instance of the dog class called dog, and afterwards we trigger both makeSound and giveBirth methods. Let's run the program and see the output. Okay, as we can see, bark and dog gives birth both were successfully printed to the console. It's important to note that an interface can extend multiple interfaces. For example, consider we have an interface called animal with method makeSound. We also have one more interface called domesticated with method goHome. And we have one more interface called domestic, which extends multiple interfaces. It extends both animal and domesticated. In order to specify that interface extends multiple interfaces, we need to specify the comma-separated list of interfaces after the extends keyword. Also, the domestic interface has its own method called beFriendly. So, in this example, the domestic interface extends both the animal and domesticated interfaces, and this means that any class that implements the domestic interface must implement the methods from both of its parent interfaces, as well as any additional methods defined in the domestic interface. So, we also have a class called domestic dog that implements domestic interface, and this class must implement all of the methods from the domestic interface and from all of its parents. So, it also needs to implement the makeSound method from the animal and goHome method from the domesticated. Here we provided all the implementations for all of these methods. For makeSounds, we'll print bark, for beFriendly, we'll print I'm friendly dog, and for goHome, we'll print going home. So, in the main method of the main class, we simply create an instance of the domestic dog class and trigger all of the methods. So let's run this program and see the output. Okay, so we can see the outputs from all of the methods. By extending interfaces, we can create more specific and complex interfaces that build upon existing ones. This allows us to create a hierarchy of abstractions, making it easier to organize our code and create reusable components. Now, let's talk about default methods. Java 8 introduced the concept of default methods in interfaces. Default methods allow the definition of methods with a default implementation in the interface itself, rather than forcing the implementing class to provide the implementation. This is a useful feature when you want to add new methods to an interface without breaking existing implementations of the interface. Let's see the following example to understand it better. So we have an interface called vehicle, within which we have a getSpeed method. This is an abstract method, meaning that any class implementing the vehicle interface must provide an implementation for this method. It returns the speed of the vehicle as double. Also, we have a getFuelType method. This is a default method which provides a basic implementation that can be used by any class implementing the vehicle interface. In this case, it returns the string petrol. If an implementing class doesn't override this method, it will inherit this default implementation. In order to specify that the method is default, we need to use the keyword default before the return type of the method. Also, we have a print speed method. This is another default method that prints the speed of the vehicle to the console using the getSpeed method. Like the getFuelType method, implementing classes can either use the default method as is or override it to provide their own implementation. Please note that here within the default printSpeed method, we use the abstract getSpeed method. We also have an implementation class called car. Class car implements the vehicle interface. We have defined a constructor for the class car that accepts double to set the speed to the car. And also the car class provides an implementation for the getSpeed method as required by the vehicle interface. Since car doesn't override the getFuelType or printSpeed, it inherits the default implementations provided by the vehicle interface. So let's see the usage example. We have a main class within which we create a myCar object. Afterwards, we call the default printSpeed method. And after that, we print the result of the getFuelType method call. Key points in this example are the following. The vehicle interface provides default methods getFuelType and printSpeed that can be used by any implementing class. These methods offer a convenient way to add common functionality across multiple classes without requiring each class to implement them individually. And also, while default methods provide a basic implementation, they can be overridden by any implementing class if custom behavior is needed. This allows us for flexibility and reuse of code. So let's run the program and see the output. Okay, we can see that the speed is 120 and the fuel type is petrol. The speed is 120 because in the default method here, we use the getSpeed method to print the speed. And getSpeed method is implemented in the car class. And it simply returns the speed we passed to the constructor. And we passed 120 to the constructor, so it was printed to the console. And fuel type petrol is printed because it's just a result of the default implementation. So within the default implementation, the fuel type is petrol. By using default methods in an interface, you can define shared behavior across different classes while still allowing those classes to provide their own specific implementations where necessary. This makes your code more modular and reduces duplication, as common functionality only needs to be defined once in the interface. Next, let's talk about static methods in interfaces. Just like in classes, interfaces can also have static methods. These are methods that are shared by all implementations of the interface and do not depend on any instance variables of the implementing class. The syntax for a static method in an interface is similar to a static method in a class. Let's see a code example to understand this better. So consider we have an interface called shape with two methods, getArea and static method createCircle. The createCircle method is a static method that returns a new circle object with the given radius. This method can be called directly on the interface without having to create an instance of an implementing class, almost the same as we have with regular classes. Also, we have a circle class that implements shape, that overrides the getArea method in the following way. The implementation currently is not really important. Please focus just on the static method createCircle. Also, we have a main class within which we create a circle in the following way. We call the static method createCircle on the shape interface and passing in the radius of the circle. Since the createCircle method returns the circle object, we are able to call the getArea on this object and assign it to the variable circle area. Afterwards, we simply print the circle area to the console. Let's now run the program and see the output. Okay, we now see that the circle area is 78.53. It doesn't always mean that we need to create a new object within the static method. We can just print something to the console, for example, within the static method, like static void print, and let's print hi. And now within the main method, let's simply call shape.print and run the program. So hi will be printed to the console. So the main idea of the static methods within the interfaces is that we don't need to create any objects to call these methods. Hello and welcome to the lesson. And today we are going to dive into the topic of combining interfaces and abstract classes in Java. This is an important topic as it will give you a clear understanding of when to use interfaces and when to use abstract classes in your Java programs. In this lesson, we will start by discussing the differences between interfaces and abstract classes. So, during this lesson, we will discuss the following topics: the difference between interfaces and abstract classes, when to use interfaces and when to use abstract classes, extending an abstract class and implementing an interface, and also we'll discuss differences between implements and extends keywords. Let's start with the differences. Interfaces and abstract classes are similar in some ways, but there are some key differences that you need to be aware of. First of all, let's look at interfaces. An interface defines a set of abstract methods which are methods without a body. These methods must be implemented by any class that implements the interface. Interfaces are used to specify a set of behaviors that must be provided by any class that implements the interface. Interfaces can also contain constant variables. On the other hand, abstract classes are used to define a base class that contains both abstract and concrete methods. An abstract class can have both abstract methods and concrete methods, which are methods without a body and with a body. The abstract methods must be overridden by any concrete class that extends the abstract class. In other words, an abstract class provides a blueprint for its subclasses, and the subclasses must implement the abstract methods to make them concrete. So, to summarize, interfaces only contain abstract methods, while abstract classes can contain both abstract and concrete methods. When you use interfaces, you are specifying a set of behaviors that must be provided by any class that implements the interface. When you use abstract classes, you are providing a blueprint for subclasses which must implement the abstract methods to make them concrete. Now, the question arises, when should we use interfaces and when should we use abstract classes? Let's start with interfaces. Interfaces are used when we want to define a contract that must be implemented by multiple classes. For example, let's consider the drawable interface that defines the contract for any object that can be drawn on the screen, as at the example on the screen. As you can see, both the circle and square classes implement the drawable interface, meaning that they both must provide an implementation for the draw method. On the other hand, abstract classes are used when we want to provide a common base class with some common behavior. For example, let's consider an abstract class shape, as you can see on the screen. So as you can see, both the circle and square classes extend the shape abstract class and provide their own implementation for the area method. But they also have the rotate method that is common for all classes that extend the shape class. In summary, use interfaces when you want to define a contract that must be implemented by multiple classes. And use abstract classes when you want to provide a common base class with some common behavior. Let's discuss how we can extend an abstract class and implement an interface at the same time in Java. This is a common scenario that can arise in real-world applications. Let's start by understanding why we would want to do this. Imagine that we have a base abstract class that defines some common functionality and an interface that defines some required behavior. We may have a concrete class that needs to inherit the functionality of the abstract class and also implement the behavior defined by the interface. This is where extending an abstract class and implementing an interface comes into play. It's also possible for an abstract class to extend another abstract class. In this case, the subclass must implement the abstract methods defined in both the parent abstract class and the grandparent abstract class. In conclusion, extending an abstract class is a key concept in object-oriented programming with Java. It allows you to create concrete classes that inherit the properties and behavior defined in the abstract class, while still being able to add their own unique behavior. Let's take a look at some code to better understand this concept. So, in this example, we have an interface named shape that defines a method draw. We also have a base shape abstract class that defines a method printinfo that simply prints the following string to the console. Finally, we have a concrete class named circle that extends base shape and implements shape. So, the class circle inherits the functionality of the base shape abstract class, meaning that it has access to the printinfo method of the base shape class. The class also implements the draw method from the shape interface. By extending an abstract class and implementing an interface, we can achieve code reusability, maintain separation of concerns, and provide a clear definition of what is expected from concrete classes that inherit from the abstract class and implement the interface. Let's also open the main class with the main method. Here we simply create an instance of the circle class and call the draw and the printinfo methods. Let's run the program and see the output. Okay, so we can see that both outputs were successfully printed to the console. In summary, combining the use of abstract classes and interfaces can be a powerful tool in Java programming. In the next part, we'll be discussing the differences between the keywords extends and implements in Java, so stay tuned. Let's cover the differences between the implements and extends keywords. Both implements and extends keywords are used in Java to inherit properties from other classes and interfaces. However, the way they work and the results they produce are different. The implements keyword is used by a class to inherit from an interface. It is used to specify that a class adheres to the contract defined by an interface. A class can implement multiple interfaces, but can extend only one class. This is important. When a class implements an interface, it must provide an implementation for all the methods defined in the interface. The extend keywords, on the other hand, is used to inherit from a class. A subclass that extends a superclass inherits all its fields and methods, including its abstract methods. An abstract class can have both abstract and concrete methods. When a concrete subclass extends an abstract class, it must provide an implementation for all abstract methods defined in the abstract class. Let's take a look at a code example to understand the difference between implements and extends keywords. Consider the following interface. So here we have an interface named shape that defines a method named getArea. Now let's consider the following abstract class. Here we have an abstract class named two-dimensional shape that defines an abstract method called getPerimeter. Now let's create a concrete class that implements the shape interface and extends the two-dimensional shape abstract class. So in this example, the class square extends the two-dimensional shape abstract class and implements the shape interface. By doing so, it must provide an implementation for the abstract method getArea defined in the shape interface and for the abstract method getPerimeter defined in the two-dimensional shape abstract class. In summary, the implements keyword is used to specify that a class adheres to the contract defined by an interface, while the extends keyword is used to inherit from a class or an abstract class. Also, we have a main method where we create a new instance of the square class, and afterwards we print the area and the perimeter of the square. Let's run this program and see the output. Okay, so as you can see, the area is 25 and the perimeter is 20. Hello and welcome to the lesson where we'll be discussing inheritance in Java and what it means in the context of object-oriented programming. During this lesson, we will discuss the following topics: the definition and explanation of inheritance in object-oriented programming. We'll also see some examples of inheritance in real-world scenarios. We'll understand how inheritance allows for code reuse and organization. We'll discuss extending classes in Java, understanding the relationship between parent and child classes, overriding methods in child classes, the use of the super keyword, and we'll also understand the is-a relationship in inheritance. So as you can see, there are a lot of topics to discuss today. Inheritance is a fundamental concept in object-oriented programming, and it allows for the creation of a new class based on an existing class. The new class, known as child class or subclass, inherits all attributes and methods of the parent class, also known as the base class or superclass. Inheritance allows for code reuse and organization, and it helps to promote abstraction and encapsulation in your code. To illustrate the concept of inheritance, let's consider a real-world example. Let's say we have a class called vehicle. This class has attributes like the number of wheels, the number of doors, and type of engine. And it also has methods like start, stop, and accelerate. Now, let's say we want to create a new class called car, which is a specific type of vehicle. The car class will inherit all the attributes and methods of the vehicle class and add its own specific attributes and methods. For example, the car class may have additional attributes like the number of seats, the type of transmission, and the color. And it may have additional methods like open door and close door. In Java, inheritance is achieved using the extends keyword. The syntax for inheritance in Java is simple and straightforward. For example, the code for the car class that inherits the vehicle class will look like as you see at the example code. In this example, the car class is extending the vehicle class, and it is inheriting all the attributes and methods of the vehicle class. The car class can then add its own specific attributes and methods to extend the functionality of the vehicle class. In conclusion, inheritance is a powerful concept in object-oriented programming, and it allows for code reuse, organization, abstraction, and encapsulation in your code. In the next parts of this lesson, we will explore the various aspects of inheritance in more detail and see how we can use inheritance in Java to write clean and efficient code. Let's take a look at some examples of inheritance in real-world scenarios, so you can understand the practical applications of inheritance in object-oriented programming. One of the most common examples of inheritance is in the relationship between parent classes and child classes. For example, consider a class animal. This class could contain properties and methods that are common to all animals, such as ability to move and breathe. Now, let's say we want to create classes for specific types of animals, like cat and dog. We can extend the animal class to create these child classes, inheriting all of the properties and methods of the parent class, and adding any additional properties or methods that are specific to that type of animal. In this way, we can reuse the code in the parent class while still creating specific classes for each type of animal. Another example of inheritance can be seen in the relationship between a vehicle class and a specific types of vehicles like car and bicycle. The vehicle class could contain properties and methods that are common to all vehicles, such as the ability to move and number of wheels. The car and bicycle classes can then extend the vehicle class, inheriting its properties and methods, and adding any additional properties or methods that are specific to those types of vehicles. Inheritance can also be used in the relationship between a shape class and specific types of shapes like circle and rectangle. The shape class could contain properties and methods that are common to all shapes, such as the ability to calculate the area. The circle and rectangle classes can then extend the shape class, inheriting its properties and methods, and adding any additional properties or methods that are specific to those types of shapes. These are just a few examples of how inheritance can be used in real-world scenarios. By understanding the concept of inheritance, you'll be able to write more efficient and organized code, reuse code in your classes, and better model the real-world relationship between objects. In the next part of this lesson, we will look at how inheritance allows for code reuse and organization. So stay tuned. Let's learn about how inheritance allows for code reuse and organization. So, what exactly is code reuse and organization in the context of inheritance? Code reuse refers to the ability to reuse code from a parent class in a child class. This means that we don't have to write the same code again and again for different classes. We can simply inherit the code from the parent class and use it in the child class. This makes our code more efficient and helps us avoid duplicating code. Organization, on the other hand, refers to the way we structure our code. Inheritance allows us to create a hierarchical structure for our classes, making it easier for us to understand the relationships between different classes. Let's take a look at an example to see how inheritance can allow for code reuse and organization. Suppose we have a class called animal, which represents all animals. This class has the following code. So we have two properties, name and age. We have a constructor that simply sets these properties. And also we have two methods, eat and sleep, that simply prints the following messages to the console. Now, let's say we want to create a class for dogs. We can create a child class called dog and inherit the code from the animal class. The dog class will look like this. So here we specify that the dog extends the animal. So the dog is a subclass of animal. Dog has its own property called breed. It also has a constructor. Here we use the super keyword to access the parent constructor. So in the very first line of the dog constructor, we call the super constructor. So we call in the animal constructor with name and age. It means that we call the following code. So the name and age will be also set. And additionally to this, we'll also set the breed. Also, the dog class defines its own method called bark that simply prints the following message to the console. As you can see, the dog class has all the properties and methods from the animal class, plus an additional property and method specific to dogs. This is an example of code reuse. We were able to reuse the code from the animal class in the dog class, which makes our code more efficient and easy to maintain. So let's look at the main method of the main class. Here we create a new instance of the dog class and we call eat, sleep, and bark methods. So here we are reusing the code of the eat and sleep methods from the animal class, so we don't have to write the same code in the dog class. These methods are extended and the bark method belongs to the dog class. So let's run this code and see the output. Okay, we can see the outputs from all of the methods. Additionally, by creating a parent-child relationship between the animal and dog classes, we have created an organized structure for our classes. This makes it easier for us to understand the relationships between different classes and how they relate to each other. In conclusion, inheritance allows us to reuse code and create an organized structure for our classes. This makes our code more efficient and easy to maintain. In the next part of this lesson, we will dive into how to extend classes in Java and learn about the relationship between parent and child classes. It's important to note that the subclass can only access the public and protected members of the superclass. Private members are not accessible by the subclass. In addition to inheriting properties and methods, the child class also inherits the relationships and behaviors established in the parent class. For example, if the parent class has a relationship with another class, the child class will also have that same relationship. It's also important to note that a child class can only have one parent class, but a parent class can have multiple child classes. This allows for a hierarchy to be established with parent classes providing a foundation for child classes to build upon. So, What we have learned from this? Extending classes in Java allows us to inherit the attributes and behaviors of a parent class and build upon it, resulting in a more organized and reusable code. To start, let's consider a simple example. Let's say we have a parent class called vehicle with a method called move, which displays the vehicle is moving to the console. Now, let's say we have a child class called car that extends the vehicle class. If we want the car class to have its own implementation of the move method, we can override the method in the car class. The updated implementation could display the car is moving instead of the vehicle is moving. When we call the move method on an object of type car, the output will be the car is moving, even though the method is originally defined in the parent class. So let's go to the main method, where we create a new object, new instance of the car class, and call the move method. The child class, car, has overridden the behavior of the parent class method, which is one of the key advantages of inheritance. It's important to note that the child class method must have the same method signature as the parent class method in order to override it. The method signature includes the method name, the number of arguments, and the types of arguments. Additionally, when a child class overrides the method, it also requires to use the override annotation in Java. This annotation serves a reminder that the method is meant to override a parent class method, and it helps to catch errors if the method signature is not the same as the parent class method. So far, we've seen how inheritance allows us to reuse code from a parent class and extend its behavior in the child class. Overriding methods is a key aspect of this process and helps to keep our code organized and maintainable. So let's run this program and see the output. Okay, so we can see that the car is moving. Not the vehicle is moving, but the car is moving because we've overridden the method. Let's learn about the super keyword in inheritance in Java. The super keyword is used to refer to the parent class in inheritance. It allows you to call methods and access variables from the parent class in a child class. This can be useful when you want to reuse or modify the behavior of the parent class. In Java, the super keyword serves several important purposes, especially in the context of inheritance. It's used to refer to the immediate parent class of a class. So let's discuss the first usage of the super keyword. So the first usage is when a method is overridden in a subclass, you can still call the version of the method defined in the superclass using super. So let's consider the following example. Here we have a class called parent with single method called display, which simply prints display method in parent to the console. Also, we have a child class that extends parent. Here we also have a display method. We need to specify the override annotation. And here within the display method, we call the super display. And afterwards, we print display method in child to the console. So this line calls display method of parent class. So when we call the display method of the child class, it will first call the display method of the parent class and will print the following message to the console, and afterwards it will print the following to the console. So let's run the program where we create a new instance of the child class and call the display method. Let's run this program and see the output. Okay, so as you can see that display method in parent was printed first, and only after that display method in child was printed. One more usage example of the super keyword. Super can be used to explicitly call a superclass's constructor. This is particularly useful when a class has multiple constructors and you want to specify which one the subclass should use. So let's consider the following example. We have a class called parent with two constructors. First one doesn't have parameters, and second one has parameters x and y. And within the first constructor, we simply print the parent constructor to the console, and here in the constructor with parameters, we print the parent constructor with parameters. We also have a child class that extends parent with its own constructor. Here, let's ignore this comment for the time being. In the very first line, we call the super constructor. It means that we call the constructor of the parent class with the following parameters: x and y, 1 and 2. So when this line is executed, the following constructor will be called, and the following message will be printed to the console. And finally, we print the child constructor to the console. We also have a main class with the main method where we simply call the constructor of the child class using new operator. So we call new child here. Let's run this program and see the output. As you can see, the parent constructor with parameters was called first. This is because at the very first line of the child constructor, we call the parent constructor with parameters. And afterwards, the system out print line statement was executed from the child constructor. Also, please note that if we don't call any other constructor here, so if I comment this line out, so let's imagine that we don't have this line, then default constructor without parameters will be called automatically under the hood by Java. So in this case, the parent constructor without parameters will be called, and the following message will be printed to the console, and only after that the following message will be printed. This is equivalent if we just called the super constructor without parameters here. But we can remove it and run the main program once again. Okay, so you can see that the message from the unparameterized parent constructor was printed first, and only after that the message from the child constructor was printed. So even if we didn't specify the super keyword here, under the hood, Java triggered the unparameterized constructor. And one more usage of the super keyword is accessing parent class field. If a field is hidden in the subclass, for example, a field in a subclass has the same name as a field in the superclass, super can be used to refer specifically to the superclass field. So consider the following example. We have a class called parent with a single property called number with value 100. Also, we have a child class that extends parent, and it has its own number property with value 200. So here we also have a show method, and we want to print the superclass number first, and after that we want to print the subclass number. In order to get access to the super number, we use the keyword super, and after that we access the number field. And if we simply use number without the super keyword, the number from the child class will be used. So within the main method, we simply create new instance of the child class and call the show method. Let's run this program and see the output. Okay, here you can see that superclass number is 100 and subclass number is 200. This is because we use the super keyword to access the parent class's number. But please note, if we remove the number from here, from the child class, then both supernumber and number will reference to the same number because child doesn't have its own number. So basically, supernumber and this number are the same because they are taken from the parent, since child class doesn't have its own number property. So in this case, if we rerun the program, both outputs will be 100. Let's discuss the is-a relationship in inheritance. The is-a relationship is a fundamental concept in inheritance, which defines the relationship between a parent class and a child class. It's the relationship that indicates that the child class is a specialized version of the parent class. In other words, the child class is a subtype of the parent class. Let's take an example to understand this relationship. Consider a class called animal. Now let's say we have a class called cat, which extends the animal class. This means that the cat class is a subtype of the animal class. We can represent this relationship by saying a cat is an animal. The statement is the is-a relationship between the cat class and the animal class. In Java, the is-a relationship is represented by using the extends keyword. For example, to create the cat class as a subtype of the animal class, we write the following code as you see at the screen. It's important to understand the is-a relationship because it allows us to take advantage of inheritance in our code. We can reuse the code in the parent class and add new functionality in the child class. This helps us to create more organized and maintainable structure. And welcome to the lesson where we'll be discussing the polymorphism in object-oriented programming. During this lesson, we will discuss the following topics: the definition and explanation of polymorphism in object-oriented programming, how polymorphism allows for flexibility and dynamic behavior in code, understanding the difference between overloading and overriding methods, and we'll also see some examples of polymorphism in use, such as with the instance of operator. Polymorphism is a fundamental concept in object-oriented programming that refers to the ability of a single function, method, or operator to perform different tasks depending on the context in which it's called. In other words, polymorphism allows for objects of different classes to be treated in a similar manner as long as they implement the same interface or extend a common class. This enables code to be written in a more flexible and reusable manner, and it can work with multiple types of objects without needing to know exactly what type they are. Polymorphism is achieved through dynamic dispatch, which determines the implementation of a method to call at runtime based on the actual type of an object rather than its declared type. In simple terms, polymorphism refers to the ability of an object to take on multiple forms. In object-oriented programming, polymorphism is achieved by allowing objects of different classes to be treated as objects of a common class. This is achieved through the inheritance and the use of interfaces and abstract classes. Let's consider an example to better understand polymorphism. Let's say we have a class called animal, and also we have two subclasses, dog and cat. The animal class contains a method called makeSound, which easily prints the following message to the console: the animal makes a sound. And each subclass, like dog and cat, override this method to provide a different output. Like for dog, we print the dog barks, for cat, we print the cat meows. So in this example, we can see that the dog and cat classes are both subclasses of the animal class, and both override the makeSound method to produce a different output. This is a polymorphism in action. Now let's go to the main method. And let's say we have an array of animal objects. So at index 0 of the animals array, we have an animal object. At index 1, we have a dog object. At index 2, we have a cat object. And we specified that the type of the animals variable is array of animals. We are able to do that because animal is parent for all of them, for the cat, for the dog. And now let's say we want to call the makeSound method on each object in the array. We can do this without knowing the exact type of each object in the array, as the makeSound method will be called dynamically at runtime based on the type of each object. So here we have a for each loop, and for each animal in the animals array we call the makeSound method. Let's run this program and see the output. And we can see that the animal makes sound was printed, the dog barks, and the cat meows was printed. This is a simple example of how polymorphism allows for flexibility and dynamic behavior in code. By using polymorphism, we can write more efficient and reusable code without having to write separate code for each type of object. Let's discuss the difference between overloading and overriding methods in polymorphism. Overloading and overriding are two common concepts in polymorphism, and it's important to understand the difference between the two. Overloading refers to having multiple methods with the same name but with different parameter lists in the same class. This means that you can have multiple methods with the same name but with different arguments or parameters. Let's take a look at an example to better understand this concept. You can see the example at the screen. In this example, the mass operation class has two methods with the same name, add, but with different parameters. The first method takes 2 parameters, while the second method takes 3 parameters. This means that you can call either method based on the number of arguments that you need to pass. This is called method overloading, and it's a powerful feature of polymorphism that allows for code reuse and easier readability. On the other hand, overriding refers to the ability of a subclass to provide a different implementation for a method that is already defined in a superclass. This means that you can override a method in a subclass to provide a different implementation for that method. Overriding allows for greater flexibility and dynamic behavior in your code, and it allows you to change the behavior of a method at runtime based on the object that is calling the method. Let's take a look at an example to better understand this concept. You can see the example at the screen. In this example, we have a shape class that has a method called draw. We also have a circle class that extends the shape class and overrides the draw method. This means that when we call the draw method on a circle object, it will call the overridden method in the circle class, which will print draw in a circle. If we call the draw method on a shape object, it will call the draw method in the shape class, which will print draw in a shape. It's important to note that when you override a method, the method signature or the name and the parameters must be the same in both superclass and the subclass. This is because the overridden method must have the same interface as the original method in the superclass. In conclusion, overloading and overriding are two important concepts in polymorphism that allow for greater flexibility and dynamic behavior in your code. Overloading allows for code reuse and easy readability, while overriding allows for greater flexibility by allowing you to change the behavior of a method at runtime based on the object that is calling the method. Let's discuss some real-world examples of polymorphism in use, specifically with the instance of operator. Let's first start by understanding the instance of operator. The instance of operator is a way to determine the type of an object at runtime. It is a Boolean operator that returns true if an object is of the specified type or false otherwise. The syntax for using the instance of as it follows. You can see it on the screen, where object is an object reference and type is the type of class that we want to check the object against. Now, let's see an example of polymorphism in use with the instance of operator. Let's consider a scenario where we have a superclass called animal, as in the previous example with method makeSound, and also we have subclasses dog and cat that override the makeSound method, respectively. And now let's say we have an array of animals as in the previous example. And we want to call the makeSound method on each object. But we also want to determine the type of each object before calling the makeSound method. This is where the instance of operator comes into play. So in this example, we are using the instance of operator to check the type of each object in the array and then calling the appropriate makeSound method. So here we check that if animal is instance of a dog, then we print dog object. If it's an instance of a cat, we print cat object, and otherwise we print animal object. So let's run this program and see the output. So as you can see, the instance of operator allows us to determine the type of an object at runtime and use that information to call the appropriate method. This is a powerful feature of a polymorphism that provides us with flexibility and dynamic behavior in our code. Hello and welcome to the lesson where we'll be discussing advanced inheritance and polymorphism. During this lesson, we will discuss the following topics: understanding the use of the final keyword in classes and methods, understanding the use of the protected access modifier, understanding the difference between composition and inheritance, understanding the use of inner classes and anonymous classes in polymorphism, and understanding the use of typecasting and downcasting. First, let's dive into the use of the final keyword in classes and methods. The final keyword is a modifier that can be applied to classes, methods, and variables in Java. When a class is declared as final, it means that it cannot be subclassed. That is, no other class can extend or inherit from a final class. When a method is declared as final, it means that it cannot be overridden by subclasses. When a variable is declared as final, it means that its value cannot be changed once it has been assigned. For example, consider the following code. We have a class car and we have a class sports car that extends car. Let's update the car class in the following way. Let's add the final modifier before the class keyword and let's go to the sports car. And now we can see that compiler argues that cannot inherit from final class car. So as you can see, trying to extend a final class will result in a compile time error. This is useful in situations when you want to prevent a class from being subclassed, as it helps ensure that the implementation of the class remains consistent and cannot be changed by subclasses. Similarly, when a method is declared as final, it means that it cannot be overridden by subclasses. That is, subclasses cannot change the implementation of a final method. For example, we have a class car with method startEngine, and we have a child class sports car that extends car, where we override the startEngine method. Let's update the car class in the following way. let's add the final modifier before the return type of the method. Let's go to the sports car, and now, as you can see, trying to override a final method will result in a compile time error. This can be useful in situations where you want to ensure that a particular method always behaves in a specific way. In addition to classes and methods, variables can also be declared as final. When a variable is declared as final, it means that its value cannot be changed once it has been assigned. For example, we have a class car where we have an integer field called number of wheels, where we immediately assign the value of 4. We also have a method change number of wheels, where we update the value of the number of wheels variable. If we want to make the variable number of wheels final, we need to add the final modifier before the type of the variable. And as you can see now, compiler argues that we cannot assign a value to final variable number of wheels. In conclusion, the final keyword can be a powerful tool for ensuring the consistency and stability of your code. By declaring classes, methods, and variables as final, you can ensure that they cannot be changed in unexpected ways by subclasses. Let's dive into the use of the protected access modifier in Java. As you already know, access modifiers control the accessibility of class members, such as fields and methods, to other classes. There are 4 access modifiers in Java: private, default, protected, and public. Today we'll focus on the protected access modifier. The protected access modifier is similar to the default or package private access level. However, it has a key difference. Members declared as protected are accessible not only within the same package, but also from subclasses that are located in different packages. In other words, protected access modifier allows for members to be accessed from a subclass even if it's located in a different package. Let's consider the following example to understand the use of the protected access modifier. We have a class called animal with a protected field called number of legs, and a method called getNumberOfLegs that returns the value of the number of legs field. Now, let's open one more class we have. It's called mammal. And the mammal is a subclass of the animal class. It's located in the very same package as the animal class, section 4.lesson10.example4. The mammal class can access the number of legs field and the getNumberOfLegs method of the animal class because it's a subclass and located in the same package. Now let's look at the following class. We also have a class called fish, and it's located in a different package, section 4.lesson10 example4.ocean, and you can see it from the structure here. So animal and mammal are located in the example4 package, and fish is located in the ocean package. As you can see, the fish class can also access the number of legs field and the getNumberOfLegs method, even though it's located in a different package, because they are declared with the protected access modifier. So here we can also use the number of legs field and we will have access to it. And we can assign a different value to it, for example. In conclusion, the protected access modifier is useful when you want to allow subclasses to access members that are not accessible to other classes. It is a step up from the default access level, as it allows for members to be accessible to subclasses even if they are located in different packages. I hope you now have a better understanding of the use of the protected access modifier in Java, and if you have any questions, feel free to ask. Let's discuss the difference between composition and inheritance. As you may already know, inheritance is a mechanism in object-oriented programming that allows a subclass to inherit the properties and behaviors of its superclass. The subclass can also add or override properties and behaviors as needed. Composition, on the other hand, is a mechanism in object-oriented programming where an object is created from other objects. In other words, instead of inheriting properties and behaviors from a superclass, an object is composed of other objects. Let's take an example to understand this concept better. Suppose we have a class car and engine. A car has an engine. In inheritance, we would create a subclass car engine that inherits from engine. In composition, we would create a class car that has an object of engine. Here's what the code would look like for inheritance. You can see it at example 1 from the left side. And here what the code would like for the composition from the right side. As you can see, the main difference between inheritance and composition is that inheritance creates a subclass and composition creates an object. Both inheritance and composition have their own advantages and disadvantages, and the choice between the two depends on the specific requirements of the project. In general, inheritance is used when there is a clear inheritance hierarchy, and composition is used when objects are required to be composed of other objects. However, it's important to know that inheritance can lead to tight coupling between classes, while composition allows for more flexibility and loose coupling between objects. In conclusion, inheritance and composition are two important concepts in object-oriented programming that provide different mechanisms for creating objects. Understanding the difference between the two and when to use each is an important part of being an effective Java programmer. Let's focus on inner classes. So what exactly are inner classes? Inner classes are classes that are defined inside of another class. They are sometimes referred to as nested classes. Inner classes can be either static or non-static, and they provide a way to group classes together and encapsulate them within a larger class. One of the main benefits of using inner classes is that they can access all of the instance variables and methods of the outer class, including private variables and methods. This means that you can write more concise and readable code. Let's take a look at a simple example. Suppose we have a class called person and we want to define a nested class within it called address. So the code will look in the following way. As you can see, the address class is defined within the person class. To create an instance of the address class, we first need to create an instance of the person class. Like this, we have a main class with the main method, and first we create an instance of the person class. And after that, we use the following syntax: person.address, we define the name of the variable, and we use person.new address. You can see that we need to use the new keyword twice, once to create an instance of the person class and once to create an instance of the address class. It's important to know that inner classes can have their own instance variables and methods, just like any other class. And just like other classes, inner classes can also be instantiated, passed as parameters to methods, and returned from the methods. So that's an overview of inner classes in Java. I hope this helps you understand this powerful concept and how it can be used to write more concise and readable code. In this part of the lesson, we'll be talking about anonymous classes, so stay tuned. An anonymous class is a type of inner class that doesn't have a name. Anonymous classes are used when we need to create a short and simple implementation of a class or an interface, usually for a one-time use. In this way, anonymous classes are a more concise way to write short classes rather than declaring a separate named class for every use case. Here is a simple example to illustrate the concept of anonymous classes in Java. Let's say we have an interface called greeting with a single method, greet. Now let's create an instance of the interface using an anonymous class. Here we have a main class with the main method, and here, in order to create an instance of the interface using an anonymous class, we use the following syntax. We define a new variable called hello of type greeting, and we assign it the following value: new greeting, and after that we have brackets within which we need to override the greet method. If we had more methods within the greeted interface, we need to override all of them. And afterwards, we call the greet method on the hello object. So the output will be hello. Let's run this program and see the output. Okay, as you can see, the output is hello as expected. So in this example, we create an instance of the greeting interface using an anonymous class and implement the greet method right on the spot. This is how anonymous classes are used to implement interfaces. Similarly, we can also use anonymous classes to extend a class. For example, we have a class called hello world with single method greet, which simply prints hello world to the console. And in the main class, in the main method, in the very same way as for interfaces, we use an anonymous class to override the greet method. And afterwards, we call the greet method on the hello world object. So it will print hello from anonymous class to the console. Let's run this program and see the output. Okay, we can see hello from anonymous class. So in this example, we extend the hello world class with an anonymous class and override the greet method. This is how anonymous classes can be used to extend a class. It's important to note that anonymous classes cannot have a constructor. Also, since anonymous classes have no name, they cannot be accessed outside of the scope in which they are declared. In conclusion, anonymous classes provide a concise way to write short classes for one-time use. They are used to implement interfaces or extend classes, and they are a great tool to have in your Java programming arsenal. Let's discuss the use of typecasting and downcasting. Typecasting and downcasting are important concepts in Java and are used to change the type of an object reference. Before we dive into typecasting and downcasting, let's take a look at object references and inheritance. In Java, objects are created from classes. When we create an object, we are creating a reference to the object in memory. When we refer to an object, we use the object's reference. By default, the object reference can only access members of the class to which it belongs. However, if a class is derived from a parent class, the object reference can access members of both the parent class and the derived class. This is known as inheritance. Now let's talk about typecasting. Typecasting is the process of changing the type of an object reference. This is useful when we want to access members of a parent class that are not available in the derived class. Typecasting is done using the cast operator, which is written as type in brackets. For example, consider the following code. We have a class called animal with a single method, make sound. Also, we have a class dog that extends animal and has its own method called bark, so animal doesn't have a bark method. And here we simply print the dog barks to the console. Let's open the main class, and within main method we do the following. We create an object of a dog class and assign it to an animal reference. This is known as upcasting. Upcasting is always safe and can be done without an explicit cast. But here, as you can see in the comment, we are not able to call the bark method on the variable a. Let's uncomment it and make sure. So the compiler says that it cannot resolve method bark in animal. Because of this, in next line, we typecast the animal reference to a dog reference using the cast operator. So this is a cast operator. We use parentheses within which we specify a class name to which we are going to cast a reference. So this is known as downcasting. Downcasting is not always safe and can result in a class cast exception if the object being downcasted is not of the type specified in the cast operator. In our case, the downcast is successful and we are able to call the bark method on the dog object. So let's run this program and see the output. So as you can see, the dog barks was successfully printed to the console. It's important to remember that typecasting and downcasting should be used with caution. If you are unsure about the type of an object, it's always best to check the type before downcasting. This can be done using the instance of operator, which returns true if the object is of the specified type and false otherwise. In conclusion, typecasting and downcasting are powerful concepts in Java that allow you to change the type of an object reference. This can be useful when you want to access members of a parent class that are not available in the derived class. However, it's important to use typecasting and downcasting with caution to avoid class cast exception errors. Hi, and welcome to the lesson where we'll be discussing encapsulation, one of the 4 fundamental principles of object-oriented programming. During this lesson, we will discuss the following topics: the definition of encapsulation, explanation of how encapsulation works, explanation of public, private, protected, and default access modifiers, use of access modifiers in classes, methods, and variables, and we'll also see some code examples of encapsulation in practice. So, what is encapsulation? Encapsulation is a mechanism of wrapping up data and functions into a single unit called an object. This provides a way to secure and hide the implementation details of a class from other parts of the code. In other words, encapsulation is about making sure that the internal workings of a class are protected from the outside world. Encapsulation is a critical aspect of software development as it promotes the separation of concerns, allowing us to create clean, maintainable, and reusable code. The goal of encapsulation is to protect the data and behavior of an object from the outside world, ensuring that the object's state remains consistent and predictable. Let's look at an example to better understand this. Imagine you have a class called bank account that represents a bank account. This class would have data members like the account number, balance, and the account holder's name. It would also have methods like deposit, withdraw, and check balance. When you encapsulate these data members and methods within the bank account class, you can ensure that only the bank account class has access to these internal workings. This way, you can prevent other parts of the code from making accidental or intentional changes to the data members and methods, ensuring that the bank account object remains consistent and predictable. In summary, encapsulation is a fundamental principle of object-oriented programming that helps to secure and hide the implementation details of a class from the outside world, promoting the separation of concerns and allowing us to create clean, maintainable, and reusable code. One more simple example of the encapsulation can be a simple car. As a driver, you don't know what exactly happens under the hood. You just need to press the gas pedal and the car will move. And you don't need to know the implementation details of the car engine and so on. And this is an example of the encapsulation because all of the details are encapsulated under the hood of the car. To understand encapsulation, let's consider a real-world example. Consider a bank account. A bank account is a good example of encapsulation as it only allows you to perform a set of actions such as deposit, withdraw, and check balance. You cannot access or modify the account information directly. This is encapsulation in practice. In Java, we can implement this concept by declaring variables and methods as private and then providing public methods to access and manipulate these variables. Let's consider the following example. So here we have a bank account class with a private variable balance and 3 public methods: deposit, withdraw, and get balance. The variable balance can only be accessed and modified through public methods. This way, we ensure that the balance cannot be modified directly and only through the prescribed methods. So the deposit method simply updates the balance by adding the amount to it. The withdraw method has some internal checks under the hood, so it checks that if balance is greater than or equal to amount, then we are able to withdraw. Otherwise, we need to print that we don't have enough balance, insufficient balance. And finally, we have a get balance method. So let's go to the main class. Here we have an instance of the bank account class, and we call the deposit and withdraw. And as you can see, we are not able to access the balance directly and update it directly. We're only able to use the deposit and withdraw methods. Finally, we print the bank account balance. Let's run this program and see the output. Okay, so as you can see, we deposited 100, after that we withdraw 30, and finally our balance is 70. So this is how encapsulation works in Java. By restricting access to the internal details of an object and only exposing a public interface, we can control the way the data is manipulated and protect it from any unauthorized access or modification. Encapsulation is all about hiding the internal workings of an object and exposing only what is necessary to the outside world. And access modifiers in Java allow us to control the visibility of the members of a class. There are 4 types of access modifiers in Java: public, private, protected, and default. You're already familiar with them, but let's repeat one more time to just make sure that we understand them completely. A member declared as public is accessible from anywhere in the program. A member declared as private is only accessible within the same class. In other words, it's only accessible from within the class that defines it. A member declared as protected is accessible within the same class and any subclasses of the class. It can also be accessed from other classes in the same package. A member with default access modifier, also known as package private, is accessible within the same class and from classes in the same package. It's important to understand the access level of the members in a class because it helps in encapsulating the internal workings of the class. By restricting access to certain members, we can ensure that they are only modified in ways that we intended. Let's dive deeper into the use of access modifiers and how they can be applied in classes, methods, and variables to enforce encapsulation. First, let's start with the use of access modifiers in classes. When defining a class, you can use access modifiers to control the visibility of the class and its members. For example, if you use the public access modifier, the class can be accessed from any other class in your code. If you use the default access modifier, the class can only be accessed from classes in the same package. Let's look at a code example to see this in action. Here is a class defined with the public modifier, it's called public class. And here is a class defined with the default access modifier, called default class. Also, we have a main class, and as you can see, the main class is located in a different package. So default class and public class are located in the example2 package, and the main class is located in the main package. So they are located in different packages. So, as you can see from the comments, we are able to use the public class because it's accessible, but we are not able to access the default class because we are not able to use the class from outside package, since default class has a default access modifier. Next, let's look at the use of access modifiers in methods. When defining methods, you can use access modifiers to control the visibility and accessibility of the methods. For example, if you use the public modifier, the method can be called from any other class in your code. If you use the private modifier, the method can only be called from within the same class. So here is an icon example to understand the use of access modifiers in methods. Here we have a class called myClass with two methods. One of them has public access modifier, second one has private access modifier. Also, we have a main class with the main method where we create a new instance of the myClass and call myPublic method. But we are not able to call myPrivate method because it's private and cannot be accessed, so compiler will not allow us to compile the code. And finally, let's look at the use of access modifiers in variables. When defining variables, you can use access modifiers to control the visibility and accessibility of the variables. For example, if you use the private modifier, the variable can only be accessed from within the same class. If you use the protected modifier, the variable can be accessed from within the same class and by any subclasses and within the same package. So here's a code example to demonstrate the use of access modifiers in variables. We have a class called myClass with two variables. One of them is private, second one is protected. Also, within the main method, within the main class, we create a new instance of the myClass, and after that we want to print the protected variable and private variable. As you can see, we are able to access the protected variable, but we are not able to access the private variable. The protected variable is accessible since the main class is in the same package as the myClass, and private variable is not accessible because it's visible only within myClass. Hello everyone, and in this lesson we are going to be discussing solid principles. During this lesson we will discuss the following topics: the explanation of the acronym SOLID and its meaning, and the definition and explanation of all the solid principles. SOLID is an acronym that stands for 5 design principles that are intended to make software design more understandable, maintainable, and flexible. These principles are a set of guidelines that software developers should follow to design high-quality, scalable, and maintainable software systems. The solid principles are essential for any software developer to know and understand. In this lesson, we will cover each of the 5 solid principles in detail, but first, let's take a look at what each letter in the acronym SOLID stands for. S is a single responsibility principle, O is open-closed principle, L is Liskov substitution principle, I interface segregation, and D is dependency inversion principle. Each of these 5 principles plays a vital role in ensuring that your software design is maintainable, scalable, and flexible. In the next parts of this lesson, we will take a closer look at each principle and see how it can be applied in practice. Before we move on, it's important to know that the solid principles are not strict rules that must be followed, but they are rather than a set of guidelines that can help you to improve your software design. They provide a starting point and help you to avoid common software design problems. The single responsibility principle, also known as SRP, is one of the 5 solid principles of object-oriented design. This principle states that every class should have only one reason to change. In other words, a class should have only one responsibility. Why is this important? Having a class with multiple responsibilities can lead to a class that is hard to understand, maintain, and test. When a class has multiple responsibilities, changes to one responsibility can impact other responsibilities, making the class more prone to bugs and errors. Let's look at an example. Consider a class called bank account. So it has the following methods: deposit, withdraw, and print statement. So as you can see, this class has 2 responsibilities: managing the balance with these methods and print statements with this method. If we want to change the way statements are printed, we need to modify the bank account class. This violates the single responsibility principle. A better way to handle this would be to have a separate class for each responsibility. For example, we can have a bank account class to manage the balance and a statement printer class to handle printing statements. So let's create a new class here. Let's call it statement printer, and let's move the print statement method from the bank account class to the statement printer class. And here we need to specify the balance in the parameter in the following way. By separating the responsibilities into separate classes, our code is easier to understand, maintain, and test. Any changes to the way statements are printed can be made to the statement printer class without impacting the bank account class. In conclusion, the single responsibility principle is an important concept in object-oriented design. By ensuring that each class has only one responsibility, we can write code that is easier to understand, maintain, and test. The open-close principle, or OCP for short, is one of the 5 solid principles in object-oriented programming. It states that a software entity, such as a class, should be open for extension but closed for modification. In other words, the behavior of a class should be able to be extended or modified without actually changing the source code of the class. Why is it important? Well, think about the impact of changing code. Whenever you change the code, there is a risk of introducing bugs, breaking existing functionality, or causing unexpected behavior. By following the open-close principle, you ensure that you can change the behavior of a class without changing its source code. This makes it easier to maintain your code and also helps you to avoid introducing bugs or causing unexpected behavior. Let's look at a code example to illustrate this principle. Let's say we have a class named rectangle that has a method named calculateArea. This method calculates the area of a rectangle based on its width and height. Now, let's say we want to add the ability to calculate the area of a square as well. In order to do this, we can create a new class called square that extends the rectangle class. As you can see, we are able to extend the behavior of the rectangle class to calculate the area of a square without modifying the source code of the rectangle class. This demonstrates the open-closed principle in action. To summarize, the open-closed principle is an important solid principle that helps us to design classes in a way that they can be extended without modification. This helps to maintain code more easily, avoid bugs, and reduce the risk of unexpected behavior. The Liskov substitution principle, named after Barbara Liskov, states that objects of a superclass should be able to be replaced with objects of a subclass without affecting the correctness of the program. In other words, subtypes must be substitutable for their base types. Consider the following example. Let's say we have a class called animal and a subclass called bird that extends animal. The animal class has a method called move, and the bird class overrides this method to add the specific behavior of flying. Now, let's say we have a method that takes an animal object as an argument and calls the move method. So we've defined this method in the main class. If we pass a bird object to this method, it should still work correctly because the bird is a substitution for the animal. So here in the main method, we create a new object of the bird class and pass this object to makeAnimalMove method. So let's run this program and see the output. As you can see, bird is flying was printed. This is the essence of the Liskov substitution principle. It ensures that subclasses can be used interchangeably with their superclasses, which makes our code more flexible and easier to maintain. In conclusion, the Liskov substitution principle is a critical aspect of object-oriented design, and it helps us write better, more maintainable code. Remember that subtypes must be substitutable for their base types and always strive to follow the solid principle when writing software. The interface segregation principle states that a class should not be forced to implement interfaces it doesn't use. The principle suggests that we should break down large interfaces into smaller and more specific ones, so that classes only have to implement the methods that are relevant to their behavior. This helps to reduce the coupling between classes and increase the flexibility of the system. Let's consider a code example to understand this principle better. Imagine we have a class called employee that implements an interface called person. The interface person defines methods for eating, sleeping, and working. However, not all employees have the ability to sleep or eat. For instance, a security guard who works at night. If the employee class is forced to implement all the methods defined in the person interface, it will end up with methods it doesn't need, making the class more complex and difficult to maintain. For example, as you can see, the eat and sleep methods have an empty body within the employee class. To avoid this problem, we can break down the person interface into two smaller interfaces, eater and sleeper, and make the employee class implement only the worker interface, which contains the work methods. This way, the employee class only implements the methods it needs and is not forced to implement irrelevant methods. Let's see the example code. So first, let's define the three interfaces. First one will be eater. So let's create new interface, eater. And it will contain only one method called eat. So let's define method eat. The second one will be sleeper. Let's create new interface sleeper with only one method called sleep. And finally, let's create an interface called worker. Interface worker with only one method called work. And now let's implement the employee class. The employee class will now implement only the worker interface. So we don't need to provide the redundant implementation. And we can remove the person interface now. As you can see, the employee class only implements the worker interface, which contains the work method. By doing this, we are making sure that the employee class is not forced to implement methods it doesn't need. In conclusion, the interface segregation principle is a useful guideline that helps us create more flexible and maintainable code. By breaking down large interfaces into smaller and more specific ones, we reduce the coupling between classes and make our system more modular and easier to change. The dependency inversion principle states that high-level modules should not depend on low-level modules, but both should depend on abstractions. In other words, the dependencies in our system should be inverted, with the lower-level modules being dependent on the higher-level modules. This helps to ensure that our code is flexible and can be easily changed and maintained over time. Let's consider an example to understand this principle better. Suppose we have a class called car, which has a method called startEngine. This method starts the engine of the car. The car class depends on a regular engine class. So let's open it. We have a regular engine. It also has a method start. And also we have a turbo engine. It's a different type of engine, which also has a method start. And our car currently depends on regular engine class. This means that if we change the regular engine class, we need to change the car class as well. This is not ideal as it increases the coupling in our system, making it less flexible. Let's open the main class, and here we create two engines, regular engine and turbo engine, and we create a new instance of the car with the regular engine. But as you can see, we are not able to create a car with a turbo engine. To invert the dependencies, we can introduce an abstraction layer, such as an engine interface, which defines the contract that the engine class must adhere to. The car class can then depend on the engine interface, not on the regular engine class itself. This means that if we change the engine class, we can do so without affecting the car class as long as it still implements the engine interface. So here is a code to demonstrate this. Let's create a new interface called engine. And this interface will contain single method, void start. And now let's update our regular engine to implement the engine. Let's also update, we need to provide the override annotation here. Let's also update the turbo engine in the very same way, implements engine and override. Now let's update the car class so it will have dependency on the engine interface, and let's rename it to engine everywhere. And constructor will also take engine and set the engine variable. And when we start engine, we'll call engine start. Let's go back to the main method. And now, as you can see, we can uncomment this line and call car2 start engine. So in this example, the car class depends on the engine interface, not the regular engine class. This means that we can change the regular engine class without affecting car class, as long as still implement the engine interface. This makes our code more flexible and easier to maintain. So let's run this program and see the output. Okay, so we can see that for car 1, the regular engine started, and for car 2, the turbo engine started. In conclusion, the dependency inversion principle is a crucial principle that helps us to keep our code flexible and maintainable by inverting the dependencies in our system. This helps to reduce coupling, making our code easier to change and modify over time. Hello and welcome to the lesson where we'll be discussing how Java handles memory management. During this lesson, we will discuss the following topics: explanation of how Java handles memory management, and the role of the garbage collector in removing unused objects. Memory management is an important aspect of any programming language, and Java is no exception. In Java, memory management is handled automatically by the Java Virtual Machine, also known as the JVM. The JVM is responsible for allocating and deallocating memory to objects as they are created and destroyed. When you create an object in Java, the JVM automatically reserves a block of memory to store that object. This block of memory is known as the heap. The heap is a shared area of memory where all objects are stored. As objects are no longer used, the JVM automatically frees up the memory occupied by those objects, making it available for new objects to be created. This automatic process of freeing up unused memory is known as garbage collection. Java provides a garbage collector which is responsible for freeing up memory occupied by objects that are no longer being used. The garbage collector runs in the background, so you don't need to worry about managing memory yourself. Let's see a simple example to demonstrate how Java handles memory management. Consider the following code. In this example, we create an array of integers with 10 elements. Runtime getRuntime total memory returns the amount of memory used by the JVM. When you run this code, you will see that Java has automatically reserved a block of memory to store the numbers array. So let's run this program and see the output. Okay, so we can see the memory used by the numbers array. As you can see, Java provides a convenient and efficient way to manage memory. The JVM takes care of allocating and freeing up memory, so you can focus on writing your code without worrying about memory management. Let's take a closer look at how the garbage collector works in Java. Every object in Java is created on the heap, which is a large pool of memory where all objects are stored. When we create an object, we allocate memory from the heap, and when an object is no longer being used, the garbage collector marks it for removal. The garbage collector runs periodically, checking for objects that are no longer in use. When it finds such an object, it frees up the memory that the object was using, and the memory can be reused for new objects. It's important to understand that the garbage collector doesn't remove objects immediately when they are no longer being used. Instead, it waits until the right moment to reclaim memory, so as not to disturb the normal execution of the program. The approach helps ensure that the program runs smoothly even as the heap is growing and shrinking. So, how does the garbage collector determine which objects are no longer in use? It uses a technique called reference counting. Each object in the heap has a reference count, which is the number of references to the object. When the reference count of an object drops to 0, it means that the object is no longer being used and the garbage collector can safely remove it. Let's look at an example to better understand the process. Consider the following code. In this example, we first create two strings, s1 and s2, and assign them the values hello and world respectively. Then we reassign value of s1 to s2. And finally, we set s2 to null. When we reassign the value of s1 to s2, the reference count for the string hello drops to 0, since no references to the object remain. The garbage collector will then mark the object for removal and reclaim the memory it was using. On the other hand, the string world is still being used, and its reference count is 1, so the garbage collector will not remove it. It's important to note that the garbage collector is not a foolproof mechanism. There are situations where objects that are still being used are not referenced anymore, so they will be marked for removal. This can lead to memory leaks, which are a serious problem in software development. To prevent these issues, we need to be aware of the behavior of the garbage collector and how to use it efficiently. In conclusion, the garbage collector is a critical component of memory management in Java, responsible for automatically removing objects that are no longer being used by the program. Understanding the role of the garbage collector and how it works is important for writing efficient and stable Java code.